Hello, Anton.
Hello. Okay, yeah. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Anton Timur Jalani. So here I'm as chair of this online summer school on galaxies and cosmology 2020. On behalf of the organizing committee, it is my great pleasure to welcome you to the online summer school of galaxies and cosmology 2020. So today we would like to hear a public lecture one from Professor Joel Primack from UC Santa Cruz, USA. And this is a part of the summer school of galaxies and cosmology. This school is hosted by Astronomy Research Division, Institut Teknologi Bandung, Indonesia. So I'm truly appreciate for big efforts from the committee for this school. I also want to express my great appreciation for all lecturers from around the world for their kind willingness to give lectures in this school. I also want to say thank you for Faculty of Mathematics and Natural Sciences and also Institut Teknologi Bandung for supporting us during this school. And also I would like to say thank you for the participants from around the world, invited attendees, and also everyone who are joining us in this morning via Zoom, or also maybe some of you are joining us via YouTube. This school will be held for 2 weeks, starting from today, September 14th, until September 25th. This school will be opened by public lecture one, which will be delivered by Professor Joel Primack from UC Santa Cruz. And by the end of this school, will be closed by public lecture two by Professor Eiichiro Komatsu from MPIA, Germany. So of course, for two public lectures, everyone can joining us via YouTube, or also can register to our committee for the public lectures if you want to joining us from Zoom. So in this school, we choose the biggest mystery topics in the universe, the dark matter. So if we talk about dark matter, we still have many unanswered questions about this topic. So especially for the participants of this school, I encourage you all to explore as much as possible during this school, because we have invite many experts for these topics. So, and also especially for the participants, I would like to remind you that this school has a very tight schedule from the morning to the afternoon. Maybe sometimes the schedule will be until night. So please keep your health. Maybe you can prepare some easy yoga movements to refresh your body during a lecture, because all of the lectures and the activities will be delivered by online. And more important thing, please enjoy every lectures and every activities in this school. Okay, before we continue to our main agenda on this morning, public lecture one, I want to tell you that we will hear a welcoming speech or the message from our Dean of Faculty of Mathematics and Natural Sciences, Wahyu Sri Gutomo, PhD. Okay, please hear together.
Assalamu alaikum. May peace be granted
upon all of us. Greetings to all of you. My name is Wahyu Srigutomo, first and foremost, as the Dean of Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. I am very pleased to welcome all participants to this online summer school on galaxies and cosmology 2020, Deciphering Dark Matter from Galaxies to the Universe, which will be held from 14 to 25th September 2020. The topic of dark matter is a very important topic in modern cosmology regarding the content and evolution of the universe, how galaxies and the large-scale structures of the universe are formed requires an understanding of dark matter. Efforts to detect dark matter drive progress not only in the field of astronomy but various fields such as theoretical physics, particle physics, material and detector technology, and etc. In the end, the answer to what the main matter of the universe is will give us an understanding of who we are and what our position is in the universe. The aim of this online summer school on galaxies and cosmology is not only to transfer knowledge in this field, but also to inspire young people to pursue the study of astronomy and physics, and in the future to engage in frontier research related to cosmology. This international event is a premier platform for students and researchers to share their new ideas, original research results, and practical experiences in the theory and practice of dark matter. This summer school consists of several activities. There are 2 public lectures, 22 lectures, 1 knowledge sharing with NASA, 2 students' talks, and 4 workshops. This online summer school is a team effort, and I would like to note my gratitude and appreciation for the high commitment and hard work demonstrated by all parties in making this summer school successful, especially the astronomy research group of our faculty for its effort to ensure this event possible. We would like, of course, to express our gratitude to Professor Joel Primack, PhD, from US Santa Cruz, USA, who will be giving the first public lecture, and the title is Our Current Understanding of the Physical Universe. And we would like also send to extend our gratitude to other lecturers and participants from all over the countries. I hope not only that all participants will find that this online summer school interesting and informative, but at the same time they will have the opportunity to engage with other researchers for future research development and collaboration. Thank you, and looking forward to seeing you in the future. Thank you very much. Have a nice online summer school. Thank you very much.
Okay, thanks for Wahyu Srigutomo, our deans of Faculty Mathematics and Natural Sciences, Institut Teknologi Bandung. And now we will continue to our main agenda, the public lecture 1 that will be delivered by Professor Joel Primack, PhD from UC Santa Cruz, USA. So for this public lecture will be moderated by my colleague from Institut Teknologi Bandung, Premana Wadayanti Premadi, PhD. So for now, I will hand over this session to her, please.
Thank you very much, Anton. So ladies and gentlemen, warm greetings to all of you. Thank you for joining us in Zoom and YouTube. We hope you're all well wherever you are in the world. My name is Pramana Pramadi. I welcome you to the Bosca Observatory in the Astronomy Department of the Institut Teknologi Bandung in West Java. I'm thoroughly honored to chair this very special public lecture today. The framework of modern cosmology was constructed about a century ago. Yet it was not until high-quality, cosmologically representative data became available, and also computational work made possible massive calculation, that the development of cosmology is accelerated. Using the multi-wavelength probes, we are now tracing the detailed processes in the evolution of the universe. However, the depth of the loopback time coverage of the probe pushes new interpretation of the course of the large-scale evolution that might put the established standard cosmology to crucial tests. This lecture presents a holistic overview of our current understanding of the physical universe, including the role and nature of the so-called dark sector. Our very special lecturer today, Joel Primack, is a Distinguished Professor of Physics Emeritus at the University of California, Santa Cruz, and a preeminent cosmologist whose theoretical and computational works covers the realm of particle physics to the evolution of the large-scale structure of the universe. That means from the smallest to the largest in the universe, and from the earliest epoch of universe history to the most recent. He elaborated the ideas of cold dark matter that provide guidance to further researches in both experimental and observational arena. Professor Primack is a fellow of the American Physical Society and American Association for the Advancement of Science, and has been awarded with various prestigious prizes. The most recent is the Lilienfeld Prize. On a more personal account, many years ago, I first met Joel and Nancy, not in a cosmology conference, but in a science religion conference in Philadelphia. Joel has great insight of the universe and is deeply in tune with it. You will see. So ladies and gentlemen, please write your questions in the chat box. We try to respond to them. Let us now welcome Professor Joel Primack to the stage. Joel, please. All yours.
Okay. Okay. Can people see this okay?
Yes, thank you.
Yes, okay.
Good. So I'm delighted to be able to present this opening lecture on our current understanding of the physical universe, a rather ambitious title, which I didn't choose, but I'm happy to try to live up to it. I'm going to cover in this lecture 3 different topics: the cosmos, galaxies, and a little bit about planets at the end. So to start with, cosmos. The picture that we've been looking at is beautiful but misleading because it only shows about 1/2 of 1% of the cosmic density. The other 99.5% of the universe is invisible. So if we picture all of the density of the universe, we can picture it like this, with this giant pyramid. The largest amount is dark energy, about 70%. Cold dark matter, about 25%. And all that's left is about 5%. And that's what we call baryonic matter, the kind of matter that we're familiar with, made of protons, neutrons, and electrons. Now, most of that is hydrogen and helium, but we only see light emitted or reflected or absorbed at optical wavelengths at least by a tiny fraction of that, only about 10% of the atomic matter of the universe. So let's zoom in and talk a little bit more about the visible universe. So the bottom of the pyramid is almost all of the volume, and that represents the visible hydrogen and helium, the main component of stars and nebulae and things like that. the top little bit is supposed to represent the other visible matter, everything else except hydrogen and helium. And altogether, that adds up to only about 1/100th of 1%, 10 to the minus 4 of the universe density. This picture is based on the Great Seal of the United States. That's the back of the dollar bill of the United States. And it says at the bottom, the new order of the universe. And at the top, we've written all visible matter because we're taking some liberties with this symbol. All the stars start at the beginning of star formation in the universe with just the hydrogen and helium. And those stars and their subsequent stars generate all the other elements. So the entire periodic table of the elements, except for hydrogen and helium, is made in stars. And most of the helium came from the Big Bang itself. Only a small fraction is made in stars. Many stars in the very early universe must have been much more massive than our sun, many of them in binary star systems with other massive stars. When these stars ended their lives as supernovas, they became massive black holes. The Laser Interferometer Gravity Wave Observatory, LIGO, has now detected mergers of these massive black holes, and this confirmed predictions of Einstein's general relativity that had never been tested before. In earlier tests, we were testing general relativity on scales that can be measured by velocities. So the velocity of the Earth going around the sun is 30 kilometers a second. The speed of light is 300,000 kilometers a second. So tests of things like the perihelion shift of Mercury are tests at the scale of 10 to the minus 4 in V/c. However, when black holes are about to merge, they're going around each other at very close to the speed of light. So we're finally testing general relativity at the limit, V/c of order 1, and it's passed all of the tests. In August 2017, LIGO and the new Virgo detector in Europe announced the discovery of gravity waves, not from merging black holes, but from merging neutron stars. Data from telescopes showed that this event and similar events generate most of the heavy elements in the universe, elements like europium, which is easy to see in stellar spectra, and so it's often used as a tracer, and gold, and thorium, and uranium. This is a sonification of the first of these black hole detections. The chirp at the end is the detection of the merging of the black holes. So this is the periodic table of the elements with the color code showing how we now understand the origin of these elements. So as I was saying earlier, hydrogen and helium come right out of the Big Bang, and only a small fraction of the helium is made in stars. Most of it is from the Big Bang. But if you look at europium, for example, one of the lanthanide rare earths, or gold, they're almost all made in merging neutron stars. And thorium and uranium, for example, are made entirely in the so-called R process, the rapid neutron absorption process. And the main site for that is probably also merging neutron stars. So here's another way of thinking about the universe composition. Imagine that the entire ocean, the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. But we don't see the ocean and we don't see the ships. All we see are the beacons at the tops of the tallest masts of the biggest ships. Those are the visible components of the galaxies. And as I said before, they're mostly just hydrogen and helium with only a tiny fraction from all other atoms. So we can think of the universe as dark matter ships on a dark energy ocean. It's a double dark theory. So of course, the standard terminology is lambda CDM, lambda for the cosmological constant, or some form of dark energy, and CDM for cold dark matter. So what's the secret of cold dark matter? Back in 1982 to 84, George Blumenthal, my colleague at Santa Cruz, and I worked out the theory. It was worked on more or less simultaneously by several other astrophysicists. And this is a diagram that I first showed in lectures in 1983. So each of these curves represents the growth of fluctuations of different masses. This is 10 to the 6 solar masses, 10 to the 9 solar masses, 10 to the 12 solar masses is the third one. That's the size of, that's the mass of the halo of a galaxy like the Milky Way. 10 to the 15 solar masses, that's the mass of a rich cluster of galaxies, including the dark matter. 10 to the 18 and 10 to the 21. What you'll see is that all of these enter the horizon, that's the dashed line across the center, at about the same amplitude. That's a consequence of cosmic inflation. And after they enter, these lower mass ones don't grow very much. See how they flatten out? And that's because they're entering the universe during a period when the dominant component of the universe gravitationally is radiation. That's photons and neutrinos. Whereas the matter doesn't behave the same way, and it doesn't grow nearly as rapidly. The matter that enters the universe, the scales that enter the universe, after the universe becomes dominated by matter, they grow as fast as it's possible, which is linearly with the scale factor of the universe. The scale factor represents how much the universe is expanded. And it's the same as 1 over 1 plus the redshift. So what you see is that the small masses, 10 to the 6, 10 to the 9, 10 to the 12, pile up. But after 10 to the 15 enters the horizon, there's a similar separation. So the consequence is the cold dark matter spectrum of fluctuations. This is a scale that's basically measuring how what the mass is inversely. So it's the wave number. So it's the size or the inverse size. And so on small scales, the cold dark matter spectrum is pretty flat. And on bigger scales, especially above 10 to the 15 solar masses, it's fairly steep. And various different versions of the cold dark matter spectrum were worked out in our 1984 paper that I wrote with George Blumenthal, Sandy Faber, and Martin Rees. We worked out 2 different variants, a low density variant, omega of 0.2, that's the matter density, and omega of 1. And we said that the evidence favored the lower value, and the modern value is about 0.3. This is the data on the matter distribution, the variance, delta M over M, as a function of the mass scale. And the curve has exactly the same shape as we calculated based on pure thought back in the early 1980s. So that's evidence that this cold dark matter picture really works. These data come from all these different sorts of instruments. So it agrees with the double dark theory, lambda CDM. Even more impressive is the detailed agreement of the cosmic microwave background radiation. So the blue curve is the double dark theory, lambda CDM, with 6 adjustable parameters, most of which were already known, at least roughly, before we got data on the cosmic microwave background on these scales. And by just slightly adjusting those parameters, one gets essentially a perfect fit. Every one of these wiggles. So this is the temperature angular correlation function, the temperature polarization cross correlation function on the bottom, and the electric mode polarization angular power spectrum in the bottom right. And there simply are no discrepancies. Everything is exactly as the theory predicts. So this is very impressive. There is, however, a problem. if you look at the value of the expansion rate of the universe, the Hubble parameter, that you get when you fit all of this data in the early universe, the number you get is 67.4 with a very small error, about 0.4. This is in the standard units of kilometers per second per megaparsec. But if you look at the recent measurements on the universe on scales of about a gigaparsec, they do not agree with that. And the value that you get if you add all of these together is about 73.3 in the same units, with an error of only about plus or minus 1. The discrepancy is is a factor of 6 sigma. What I'm particularly impressed by is that different methods are giving very similar results. So the Shoes collaboration uses type 1a supernovae and Cepheid variables to calibrate the distance. The Holy Cow collaboration uses lensed quasar time delays, a completely different method. And with relatively small errors, they agree remarkably well. So there's a real discrepancy. Now, there are various proposed solutions to this problem. And after looking at the various ones that have been proposed, the one that really seems to me the most plausible is an early episode of dark energy. So that version looks like this. I hope you can see the difference between the dashed curve on the right and the wiggly blue curve. So the blue represents the contribution to the cosmic density, which always adds up to 1. The contribution of a small amount of dark energy peaking at around a redshift of about 4,000. That's about 37,000 years after the Big Bang, and lasting only about 5,000 years or so. That's enough to slightly modify the size of the universe, and the consequence is that instead of, when you fit to the cosmic background radiation, getting a Hubble parameter of 67, you get 73 in very good agreement with all of these measurements. I have to emphasize that the agreement with the cosmic microwave background data is, if anything, even better than standard lambda CDM. And a paper that my colleagues and I submitted, and we just received a favorable referee report, so it's about to be accepted. It's on the archive. Anatoly Klipin is the first author. And in that paper, we ran n-body simulations for the first time based on this lambda CDM with early dark energy. And we found that the prediction of the mass function of dark matter halos today is virtually the same as lambda CDM standard. But as you go back in time, you get more structure, about 50% more clusters at redshift 1, and several times as many galaxies in the ionization era around redshift 6 or 7. So earlier formation of galaxies, earlier formation of structure, there's some evidence that this may in fact be the way the universe really works, but the evidence is so far not completely conclusive. So this is an example of how we may have to modify our standard theory as more and more data comes in, something that Pramana, I think, was mentioning. Now, astronomical observations represent snapshots of moments in time. We don't live long enough to see galaxies evolve. We can sometimes see shorter term events like supernovae and see them evolve. But that's not the case with larger things like galaxies. And theorists have the advantage over observers that we can see things like galaxies evolve. It's the role of astrophysics theory to produce movies, both metaphorical and actual, that link these snapshots together into a coherent physical theory. We make cosmological dark matter simulations that show large-scale structure and dark matter halo properties. And we also make hydrodynamic simulations that show the evolution of galaxies and the formation of the different parts of galaxies. Let me start with the cosmological scale. So This cartoon has the drunk sitting on the stoop and saying, quarks, neutrinos, mesons, all those damn particles you can't see. That's what drove me to drink, but now I can see them. And this reminds me to warn you that we're going to be able to see the dark matter in the simulations, but all the bright regions are in fact dark. They're invisible. They neither emit nor absorb nor reflect light. We're showing them, of course, with light. So this is the expansion of a small region of the universe. And you see that the substructure is forming inside it. Regions that are higher than average density are collapsing. And now the center has stopped expanding altogether, although the outer parts are still flying away. So this is the formation of the dark matter halo of a small group of galaxies with a big galaxy in the center. Let's look at some snapshots. So we started just a little bit after the Big Bang, and it expanded and it expanded. But after about halfway to the present, about 7 billion years after the Big Bang, this halo stopped expanding and the center fell together. The outer regions are still flying away. And the difference between the colorful regions and the black outer regions is the difference between space that's been tamed by gravity and stopped expanding, and space that's expanding with the universe faster and faster under the effect of the dark energy that is dominant in the emptier parts of the universe. So the big distinction is between space that's been tamed by gravity, that's held together. That's the region that surrounds galaxies and clusters of galaxies. And the space in between those gravitationally bound regions, which is expanding faster and faster. That's wild space. Let's look more carefully at one of these dark matter halos of a galaxy like the Milky Way. So the Milky Way's visible extent is only about 100,000 light years across, about 30 kiloparsecs. But the dark matter halo of a galaxy like the Milky Way is more than 10 times larger in each of the 3 dimensions, meaning that the volume of the dark matter halo is more than 1,000 times greater than the volume of the visible galaxy. How does this structure, with all of its substructure and so forth, fit into the large-scale structure of the universe? More or less like this. So this is from one of our big simulations. We called this the Bolshoi simulation. We ran it on NASA's biggest supercomputer. This is actually a billion light year by billion light year by only about 50 million light year thick slice of the simulation. And what you see is how very filamentary the dark matter structure is. The halos that will host galaxies are these yellow dots, galaxies and groups and clusters of galaxies. And the very empty regions are the cosmic voids where there are very few galaxies. Let's visualize now a small region, only 1,000th the volume of this big simulation, about 100 million light years across. We're rotating in order to show you the 3-dimensional structure. What you see is that the dark matter halos lie along these filamentary structures. And where the filaments cross, there are much larger dark matter halos, these large white regions. The Milky Way and the Andromeda Galaxy would lie on one of the small dots. We're now zooming in so you can get a better view. And that big region that's white that the arrow is pointing at is the dark matter halo of a large cluster of galaxies. How does such a thing form? Let me show you. So these are all of the dark matter halos that end up in one of those large dark matter halos that would host a rich cluster of galaxies. You'll see that they're flowing in largely in 3 directions, which is fairly typical. Left to the center, lower right to the center, and top right to the center. You'll also notice that the dark matter halos that are forming, that are large, are quite prolate. Dark matter halos are mostly prolate. They have two short axes and one long axis. Each of the larger halos would host a galaxy. And so many thousand galaxies fall into the rich cluster of galaxies that's forming. When we run these big n-body simulations, we don't just study the formation of the structure of one large halo like this. We study the formation of all of the halos, and we make all of the data publicly available. Now, that simulation that I just showed you did not show the expansion of the universe. If we had tried to show the expansion of the universe, we would have had a bunch of pictures like the ones at the top. And the problem with that is that you wouldn't be able to see very much until the universe expanded to nearly its present size, as represented by the movie. So instead, what we do is we blow up each of these earlier eras to the same size as today. Just below the one on the left, you see how it's been expanded to be the same size as the other ones. That's called looking at the universe in co-moving coordinates, and that's quite common for astrophysics. So let me now show you a video of the evolution of a region of the universe right around where our own galaxy is located. Very early, that filamentary structure forms. We're only 1 billion years or so into the evolution. The matter moves along the filaments. The filaments thicken with time. The voids empty as time goes on. The denser regions get denser. The low density regions get lower density. Well, the video would have gone on to let us fly through the universe, but let's instead look at this picture, which is actually the picture at the bottom of a swimming pool as the light has been refracted by the ripples on the top of the swimming pool. And this is from a collection of essays by the great Russian cosmologist Jacob Zeldovich. Zeldovich says simultaneous compression along 2 or 3 axes occurs very rarely. As a rule, there's only one direction in each elementary volume that stands out among the rest. So the collapse occurs gravitationally first in one dimension, and then in a perpendicular dimension somewhat later, and possibly in a third dimension later than that. And that's how structure forms, and those filaments are the consequence of first collapse making sheets, and then a second collapse making the filaments. The sheets are also there. Zeldovich would have called them by the Russian term blini, or pancakes, is how we translate that. So that's how this complicated cellular structure gets created. And before modern computers were available, Zeldovich and his collaborators worked out the basic theory of how this sort of thing must work. So by studying the evolution of dark matter halos in large simulations, we realized that the basic pattern is that halos form along these long filaments, and they tend to be quite prolate and oriented with the filament. And they're not supported by rotation. They don't fall together. They don't fail to fall together because they're rotating, but rather because matter is coming in along the filament in both directions. And as a result, they have an anisotropic velocity dispersion. There's a higher velocity dispersion along the long axis than in the 2 perpendicular directions. And that's why they have the shape, and that's why they don't all just fall together. As time goes on and the filaments thicken, the accretion of matter becomes more spherical, and the outer parts of dark matter halos are more spherical. So at high redshift, redshift 3, the shapes are quite prolate. The ratio between the short axis and the long axis, C is the short axis, A is the long axis. The ratio for a typical halo of the mass of the Milky Way is only about 0.4. The long axis is 2.5 times longer than the short axis. And as time goes on, halos become rounder, although they're still pretty prolate, even at redshift 0. Also, notice that they are more prolate at higher masses. In fact, you can fit all of this to a single curve by taking out the mass. And we did that in this paper, which was written by two of my then PhD students, Brandon Allgood and Ricardo Flores, and also two of my other PhD students who just recently finished, Risa Wexler and James Bullock. Well, let's move on to galaxies. So as you look out in space, you look back in time because it takes time for the light that leaves galaxies long ago to reach us. So the more distant the galaxies are today, the longer ago the light must have left them, and the earlier the stage at which we see them. We call these the cosmic spheres of time. This is an illustration that we used in the popular books that I wrote with my wife, Nancy Abrams. The first sphere represents, so the center is a galaxy like the Milky Way. The first sphere represents the era when the Earth itself formed and the other planets of the solar system and the sun about 4.5 billion years ago. And what you see is that the galaxies about then look very much like the galaxies today. However, if you go back to when big galaxies are just starting to form, they don't look so similar. They're somewhat misshapen. And if you go back to when bright galaxies first start forming, before 1 billion years, up until about 3 billion years after the Big Bang, these are all images from Hubble Space Telescope, and they don't look anything like nearby galaxies. They're mostly long and clumpy. We'll come back to why that occurs. Beyond this era is the cosmic dark ages, before enough stars have formed for us to be able to see these galaxies with our current telescopes. Although the ability to see further into the infrared with a larger collecting area with James Webb Space Telescope will certainly let us see a little bit further. The very colorful sphere is the cosmic background radiation emitted about 300,000 years after the Big Bang. And the cosmic horizon is the Big Bang itself, before which we cannot see at all, even with gravity waves. Now, I want to tell you about two particular things that have been discovered in the last 20 years that are very important to take into account as we think about galaxies. One is the relationship between the stellar mass of a galaxy and the mass of its dark matter halo. And what you see is an inverted U-shaped curve with the peak about the mass of the dark matter halo of the Milky Way, a little over 10 to the 12 solar masses. Now, at the peak, the fraction of the mass of a galaxy, including its dark matter halo, that's made of stars is only about 3 or 4%. Now, that's much smaller than the ratio of the amount of ordinary matter, which is about 5% of the cosmic density, to the total mass, dark matter plus ordinary matter, which is about 30%. That's a ratio of 1/6 or 0.17, 17%. But only about 3 or 4% of the density of the galaxy, of the mass of the galaxy, is stars. What this is telling us is that the vast majority of the mass of gas that started out in the dark matter halo of a galaxy the size of the Milky Way, the vast majority never turned into stars. And the Milky Way is the most efficient. It's the peak of the stellar mass halo mass relation. As you go smaller or larger in mass, even a smaller fraction of the mass is stars. That's why it is that it's only about 10% of the ordinary matter that's visible in the form of light emitting stuff, stars and nebulae and things like that, falling off steeply on both sides. So understanding exactly how that works is one of the great challenges of modern cosmology. On the right-hand side is another major discovery It's something that we only really learned in the last 15 or so years. So each of the colors represents the star formation rate, the number of stars that form per year, as a function of the stellar mass of the galaxy, and the different colors are different redshifts. So at low redshift, what you see is that at these low masses, it's almost a straight line, almost parallel to this straight line, which is just rising linearly with the mass. So another way of plotting this would have been to plot the specific star formation rate, the star formation rate divided by the stellar mass of the galaxy, and then you get flat curves. What you also see is that you get a similar behavior, again, more or less rising linearly, although flattening out at larger masses. And it is a little bit higher as you go out in redshift, at least out to about redshift 2.5. And the other thing that this figure is only showing you by showing you these error bars, which are quite small, is that there isn't much dispersion. The majority of the galaxies at this mass, a stellar mass of 10 to the 10, are forming stars in the low redshift universe at about the same rate. Not much higher, not much lower. Most of them are within a factor of 2 above or below this curve. That's really quite remarkable. Now, here's a possible explanation for that. We published this in 2016. And what we noticed was that if you plot the log of the mass accretion rate of dark matter halos, you get these red or black curves with the dispersion, a 1 sigma dispersion, that's independent of mass and redshift, and is about the same as the observed dispersion in the rate at which stars form. Now, if you look at the previous plot that showed that inverted U-shaped curve, you also perhaps noticed that there wasn't much redshift dependence. So if you want to characterize the rate at which stars form, dm star dt, you can break that down into the part that depends on the halo mass and the part that depends, independent of redshift, and the part that depends on the change in that with redshift. And to a good approximation, you can neglect that second term. So the first term is basically telling you that the rate of star formation is proportional to the slope of that curve, dm star dm vir, m vir is the virial mass of the halo, times the accretion rate of the dark matter halo. So there's a proportionality constant, there's the accretion rate, there's the dispersion in the accretion rate, and so that tells you that the dispersion in the star formation rate should also be quite small. Not only that, but it means that you can then predict what the star formation rate is as a function of mass and redshift. Here are the predictions and there's the data, and you see it actually agrees remarkably well. The whole thing works to about a factor of 2 out to something like redshift 3, where the data is still quite good. Well, almost all the stars today are in large galaxies like our Milky Way. There's lots of small galaxies, many more small galaxies than big galaxies, but they don't have very many stars. And the really massive galaxies are quite rare, and they don't have that many more stars than the Milky Way. Nearby large galaxies are disk galaxies like ours, like this picture here on the left, or big balls of stars called elliptical galaxies. But most galaxies in the early universe didn't look anything like the Milky Way or like these big balls. Most of them are pickle-shaped and clumpy. We're just now figuring out how galaxies form and evolve with the help of big ground-based telescopes and the Hubble Space Telescope and other telescopes that let us see radiation that doesn't penetrate the atmosphere. A particularly important camera was installed on the last visit that the astronauts paid to Hubble Space Telescope in 2009. It's called Wide Field Camera 3. And the advantage of that is that it let us see ultraviolet light, but especially infrared light. Now, here we're looking at pictures of the same galaxies above and below. At the bottom, we see these galaxies as we saw them with the advanced camera for surveys, the other camera that's now on Hubble Space Telescope, which basically sees the kind of light that our eyes see. And the same galaxies just above, as we see them in H-band, 1.6 microns, with wide field camera 3. The point is that the light that we would see with our eyes from these distant galaxies at redshift 2, about 10 billion years ago, the light that we would see has been redshifted by a factor of 3, redshift plus 1. And as a consequence, all we would see is the light that started out as ultraviolet light produced almost entirely by very massive short-lived stars. So we're seeing regions of star formation. But with H-band, we can see all of the blue light and much of the intermediate to red light. In other words, the light of stars like our own. And so we can see what the galaxies really look like. And of course, the advantage is that we get to see both where the stars are forming with advanced camera for surveys, and also what the whole galaxy looks like in several different wave bands with wide field camera 3. So the first big survey that used the capabilities of wide field camera 3 is called the Candel survey. And it focused especially on what we call cosmic high noon, above redshift 1, out to a redshift of several. And it did the first survey of the very early universe, the first billion years. We can call that cosmic dawn. And we, of course, are living in cosmic afternoon. Now, I used to think, and most astronomers thought, that galaxies probably start as disks. Why would they think that? Well, Newton's laws explained why planetary orbits are elliptical, but not why the planetary orbits in the solar system are all nearly circular, lying in the same plane, and with the planets moving around in the same direction as the sun rotates. Newton, when he was asked about this, said, "It's evidence of God's handiwork." In the 1780s, Laplace, the French mathematical physicist, explained this as a consequence of angular momentum conservation as the sun and planets formed in a cooling and contracting protoplanetary gas cloud that formed a disk like the one on the right. We now see many of these protoplanetary clouds turning into planets with the aid of ALMA, the Atacama Large Microwave Telescope Array. And this is a gallery of 20 of the many observations of this sort that ALMA is producing. These are all forming planetary systems. So for similar reasons, many astronomers, and I confess I was one of them, once thought that galaxies start as disks. But Hubble Space Telescope images of forming galaxies instead show us that most forming galaxies are prolate, that is pickle-shaped. As we'll see, this is the consequence of galaxies forming in the prolate dark matter halos oriented along massive dark matter filaments, which I was telling you about a little while ago. So here's our latest paper summarizing the data. There's essentially no theory in this paper. The right-hand illustration is from one of our theory papers, but everything else here is simply observational. We find that galaxies tend to be prolate at low M-star and high redshift, and oblate, that is disky, at high masses and low redshifts, consistent with our first paper on the subject, led by Arjun van der Velde in 2014. So this implies that galaxies tend to evolve from prolate to oblate, possibly through a spheroidal stage. So if you look on the bottom, you'll see that starting at 10 to the 9 solar masses at redshifts greater than 1, a majority of all galaxies up to 10 to the 9.5 solar masses are prolate, this big blue region. And a large fraction, and in fact a clear majority above redshift 2 of galaxies up to 10 at the 10 solar masses are prolate. But when you get up to higher masses, like the mass of the Milky Way today, then the majority of them are spheroidal or disky. green or red in this diagram. This is the bottom is the new data, the new summary of the data. And the top is what we said in the 2014 paper. And what you'll see is that the prolate fraction has increased a lot, and the spheroidal fraction has increased a lot, and the Disky fraction has gone down. That's because we have better data and we've done a more complete analysis. How do we do this? If you look at an individual image of a galaxy, you cannot tell from that image, if it's a thin, narrow image like this, whether that's a prolate galaxy or just a disk galaxy seen edge on. The way we would tell is if it's a disk galaxy, there must be lots of other disk galaxies that we see in every other orientation. So we have to see every axis ratio. That's what we look for. If the galaxies are disky and we plot the ratio of the short axis of the long axis of the image versus the log of the long axis doesn't depend on how it's oriented. And then we should get a roughly even distribution of axis ratios down to whatever the thickness of the disk is. On the other hand, if they're elongated, then they'll have a long axis that's long if they're pointed this way, and a short axis that's a small fraction of that. But when we see them end on, then they'll look spheroidal. They'll have an axis ratio near 1, but on the other hand, they'll be smaller. If they're all spheroids, then they're going to have an axis ratio near 1 regardless of which orientation we see them in. So we simply did that kind of statistics using all the available data. So here we're plotting the data, axis ratio, short over long axis on the vertical axis, and the log of the long axis on the semi-major axis on the x-axis. And what you see is that there's a big hole in the upper right corner. If these galaxies were really disky, we would have to see lots of points up here, but we don't. On the other hand, if you look at higher masses at lower time, at lower redshifts, later times, what you see is that there's a more or less even distribution. Not only that, but you see these points are red and these points are blue. And red means a lot of attenuation of light. We're seeing much more red light coming through than blue light. And that's because when you look at a disk edge on, there's a lot of dust and that's absorbing the light. So these are definitely largely disky galaxies, but down here, very few disky galaxies. Notice that when you make a plot of this sort, this set of images, as you're looking down, you're seeing increasing redshift earlier times. As you look across, it's higher masses. And the evolution, as you go from low mass to intermediate mass to high mass at later times, goes diagonally. Well, now let's move on to galaxy formation simulations to try to understand more about how galaxies form, and in particular, why so many galaxies start out prolate. So this is a snapshot of the dark matter from one of these simulations. And this is the stars from the same simulation. And what you'll immediately see is that the long axis of the dark matter lines up beautifully with the long axis of the stars. Let's actually watch how this one developed. So when we run these simulations, we can store thousands of time steps, and we can make these movies that I told you about. On the left, dark matter. On the right, stars. We're keeping the coordinates of the simulation fixed. And another thing that you'll notice is that there's almost no rotation. If you look at the dark matter evolution, you'll see dark matter is flowing in on both sides. And some of that material is also turning into stars. Now, in a moment, you're going to see a galaxy suddenly appear. It didn't just pop into existence. What's happening is that there it is, it came into the volume that we're visualizing. Now it's being torqued down into the filament. And now it's going to come right through the larger galaxy, right along the plane of the filament. Here comes another galaxy coming in. Now it's coming back through the galaxy. Now it's coming back again. And now it's settling down. And now the other galaxy is going to come in. So the effect of these other galaxies coming near this galaxy is to somewhat perturb the direction of the galaxy. But it's not rotation. Again, it's the stars and the dark matter are supported primarily by anisotropic velocity dispersion. Well, this goes on for some time. Let me skip on now to the summary of what happens. So here you see that the stars and the dark matter are highly aligned. This is one view, this is a perpendicular view. And what we're showing on the right-hand side from our paper that we published in 2015 on this is that when the center of the galaxy is mostly dark matter, so this is the ratio of the mass of dark matter in the region that half the total masses, or stellar masses, located in. To the left of this vertical dotted line, the center of the galaxy is mostly dark matter dominated. To the right, it's mostly stars. These points are mostly in this region, indicating that the galaxy is prolate, elongated, pickle-shaped. But when the galaxy is dominated by stars, that's no longer the case. Then the galaxy becomes rounder, either spheroidal or disky. And this was the case with our lowest mass simulations. We studied a large group of simulations in a paper published the following year. And we also predict that these prolate galaxies will tend to be aligned with each other and with the cosmic filament. Those are small galaxies. Let me tell you about much more massive galaxies, galaxies that are Milky Way mass and up. And some of those galaxies follow what we call the fast track. We called it that in a series of papers starting in 2013, led by Guillermo Barro, who's now a faculty member, but he was then a postdoc with us in Santa Cruz. I'm going to show you several plots like this. The upper left corner is, which is empty here, is galaxies that are not forming stars, or not very much anyway, so they're quiescent, and they're rather extended. So down here, rather extended, but rapidly forming stars, the specific star formation rate, the number of stars formed per year divided by the stellar mass, is increasing downward. So this is high star formation rate, but not very compact galaxies. And these are much more compact galaxies. You can see they're mostly little dots. These are often called star-forming nuggets or blue nuggets. You'll see they're actually mostly red because of dust, but they're blue because they have lots of star formation. And when we look at subsequent images of the same size region of the universe, we can see what appears to be an evolutionary pattern, that galaxies start diffuse, become compact and star forming, and remain compact but become quenched, that is not star forming. And these very small central regions are called nuggets. So blue nuggets and red nuggets, or star forming nuggets and quenched nuggets. We also see that many of the galaxies in the compact star forming area of the diagram have a very high fraction of active galactic nuclei detected by X-rays. The very dark regions here have more than 50% of the galaxies in those regions detected by X-rays as having massive black holes that are accreting active galactic nuclei. And that's probably partly the reason that many of these galaxies evolve into galaxies that have rather little star formation. The effect of the active galactic nucleus seems to be to push gas away and prevent it from forming stars. So here's that same diagram, but now with another path shown. So first we've talked about the fast track. Compact star-forming galaxies form by starting with diffuse star-forming galaxies, that move over into the compact star forming region and then quench, stop forming stars, and then often get somewhat larger. And many galaxies evolve in a different way. They never are very compact and rapidly star forming. They're always somewhat diffuse. They're always disks usually. And they just evolve in the direction of less and less star formation and a little bit larger size. And that we call the slow track. So here's that same picture. And this is the evolution in the same kind of diagram: diffuse star forming, compact quenched, diffuse quenched. And what you see is there's the fast track. And this is an example of a slow track. So we run a bunch of different simulations with high resolution, and we see both of these patterns very clearly in our simulations. If we focus on the center of the forming galaxy, the inner kiloparsec, what we see is that for a while, not much gas is there, stars form fairly slowly, and the dark matter is still the dominant form of mass in the inner kiloparsec. But then something amazing happens. Gas rapidly flows into the center, stars rapidly form, the stellar mass is bigger than the dark matter mass, and then stars stop forming in the center. It becomes a quenched nugget. And that's because gas has either been converted into stars or driven out by the effects of the supernovae. And the consequence is that there's very little happening in the center of the galaxy anymore. If we look on the whole galaxy, however, what we see is that the galaxy is still dominated by dark matter, but the amount of stars keeps growing. The amount of stars in the center hasn't changed much, but these are stars that are forming on the outside, and these are often in the form of a disk. We can actually watch how this works in simulations. I'm only going to have time to show this to you once, I'm afraid, and it moves very fast. But we've published a number of papers on this, and we have lots of snapshots and even videos online. So here what I'm going to show you is gas and stars face on and edge on. We're going to watch as these things evolve from redshift about 4.5 to about 3.5 or 3. And this region here is the compaction region. That's when the gas jumps up rapidly. You get a big increase in stars, and even on a scale of 5 kiloparsecs, larger than just the center, the stars start to become more important gravitationally than the dark matter. If you just focus on the inner kiloparsec, there's this big jump in gas in what we call the compaction region, and that results in a rapid increase in the amount of stars. So let's watch how all of this happens. So we're getting close to compaction. Okay, now there's a big inflow of gas. See all of that gas appearing? A lot of new stars have formed. Notice how the center is now very bright with stars. But from then on, we're not showing that in the video, hardly any new stars are forming in the center, and not that much, even going out to 5 kiloparsecs. But it turns out in this simulation, as you go out to larger distances, 10 kiloparsecs, there's still considerable star formation. So remember I told you about the main sequence, the fact that galaxies tend to form stars at a rate just proportional to their mass. So let's now look at the evolution of a single galaxy. And it tends to go above and below the main sequence, often several times. So it goes above when there's a flow of gas into the center, then the gas is driven out and the center stops forming stars, but sometimes more gas can come back in. And then there can be another burst of star formation, lots of supernovae going off. Maybe the active galactic nucleus gets energized, and that drives gas out. And from then on, the galaxy shuts down. So sometimes the galaxy can get rejuvenated again. So we see all of these kinds of things happening in the simulations, and I think also in the real universe. So how do we compare many simulations, thousands of snapshots from simulations, to 100,000 images from Hubble Space Telescope? And the answer is, you're not going to do it by eye. You have to train a computer. So we trained a computer, a so-called deep learning code, by giving it images of, realistic images of galaxies that we created with our supercomputer simulations, taking into account stellar evolution and also the way the dust scatters the light and absorbs, especially the shorter wavelengths. We also put in realistic noise from Hubble Space Telescope images. Once we trained the computer, we then checked it to see if it could actually distinguish correctly the different stages of galaxy evolution, and we found that it could. We then used this trained deep learning code to analyze images from Hubble Space Telescope. So this is what our images look like if we look at these galaxies as if we saw them close up. This is what these same images would look like if we degrade the Hubble Space Telescope resolution, but don't add noise. We then also have to add noise. And this is real Hubble Space Telescope images, a pickle-shaped galaxy, a spheroidal galaxy, and this is a disk galaxy. So, and these are correctly identified by the deep learning code. So here's a little video that shows how this works. There's the blue nugget stage. The gas is flowed in. The stars are now more important than the dark matter in the center. These are not real galaxies. These are simulated galaxies. Now, as I said, sometimes you can have 2 compaction events. Sometimes you can even have 3 compaction events. When there's just one compaction event, the code does a pretty good job. Green high means high probability that we're in a compaction zone. Red high is post-compaction, post-blue nugget. So this worked out pretty well. However, when you have 2 of these compactions, represented by the yellow band and the blue band, the code gets somewhat confused, understandably. Nevertheless, overall, it did a pretty good job. So what we found was that the galaxies tended to go through the compaction, the blue nugget stage, somewhere between a mass of 10 to the 9.5 and 10 to the 10 or 10 to the 10.2. A little bit higher mass at slightly higher redshift. And that's a common theme, that galaxies that end up higher mass today have gone through their evolution at an earlier time. This is sometimes called downsizing. Here, I'm showing you images that we've simulated for Hubble, and then exactly the same galaxy. This is actually a merging pair of galaxies with other stuff going on. And here we're modeling what JWST, James Webb Space Telescope, would see. And here we have this somewhat confused pattern when we have 2 of these compaction events. And with James Webb quality images, it'll be much easier. There you see that our code perfectly distinguishes. It says, yep, here we're in a blue nugget stage, no longer a blue nugget stage. Now we're definitely in a post blue nugget stage. Now we're in a blue nugget stage again, and then in a post blue nugget stage. So deep learning does much better when we have images of James Webb quality. And we hope that James Webb goes up later next year. And of course, it's being slowed down by the COVID crisis. So remember that we focus on cosmic high noon. We also have some data on cosmic dawn that I haven't had time to talk about, but we live in the late afternoon. And the universe behaves rather differently if you look at redshifts less than 1, the last 7 billion years, and not the first 7 billion years. So for example, if you look at a smaller galaxy, a galaxy that today only has about 10 to the 9 solar masses of stars and a total mass of its dark matter halo of about 2 times 10 to the 11 solar masses, it becomes a nice disky galaxy. It's not prolate. the stuff I told you about the range of masses for polate galaxies was above redshift 1. Now we're less than redshift 1. And this galaxy has a ratio of the velocity dispersion to the rotation velocity as measured by the H alpha line in its gas that's falling smoothly from about 0.4 at redshift 1 down to about 0.15 or 0.1 at low redshift. And the red points are observations, not these. This is artificial simulation. And you see that the blue curve and the red points from observations agree remarkably well. This makes a nice disk galaxy, nice thin disk. There it is in its gas, there it is in stars. Let me just spend a couple more minutes before we finish talking about planets. I think I've been talking for just a little over an hour and I have a few more minutes to go. So most of what we've learned about extrasolar planetary system has come from the Kepler Space Telescope, which stared at about 100,000 stars for several years, looking for transits, for stars crossing, for planets crossing in front of those stars. We've also discovered several hundred stars, several hundred planets around stars by looking at the reciprocal motion of the star as the planet moves around it. Because of course, the star and the planet are going around their mutual center of mass. We used to think that extrasolar planetary systems would look much like our own solar system, with all of the planets in nice circular orbits, rather spread out, with gas giants on the outside. Well, we've seen hardly any systems that look like that. There may be galactic habitable zones, not too close to the galaxy center where there are frequent supernovae, nor too far from the galaxy center where metals, that's what we call everything but hydrogen and helium, are too rare to form rocky planets. Of the roughly 4,000 planetary systems we've discovered so far, we haven't found any that's really like ours, with the planets widely spaced in circular orbits. Those that we see that are as large as the orbit of the Earth or Mars, the orbits are almost always quite elliptical, which of course would make it very difficult for living creatures to have to deal with such drastic changes in the amount of flux. Most planetary systems are much smaller, up close to their star. The most common type of planet seems to be 2 to 6 times Earth mass, called a super-Earth, but no such planet exists in our solar system. Some planets are in the habitable zone around their stars, that is, where water would be in liquid form. But most of those planets are probably not hospitable to advanced forms of life. For one thing, they might not have an optimal abundance of the long-lived radioactive elements thorium and uranium to power a magnetic dynamo and plate tectonics. The main source of heat for the Earth is radioactive heat from uranium and thorium. But the amount of uranium and thorium in different solar system, planetary systems is quite variable because these are made in extremely rare events that I told you about earlier. These merging neutron stars seem to be the main source. And although ordinary supernovae occur several per 100 years in a galaxy the size of the Milky Way, these merging neutron stars occur only every million years or so. So they're much less common. And that results in a much bigger dispersion in the amount of the radioactive elements traced by europium, which is easier to see in stellar spectra. So our living Earth may be a rare planet. There's at least when I was a kid, I read the Goldilocks story about a little girl with golden hair who goes into a bear's home, and the bears aren't home, and she sees 3 different bowls of porridge. One is too hot, one is too cold, and one is just right. And Earth is just right. There's evidence that there was a late drop bombardment of the inner planets about 750 million years after the solar system formed. It seems likely that there was a gigantic rearrangement of the outer solar system that caused many comets to hit the inner planets during that period. Primitive microbes got started on Earth soon after the late great bombardment. So primitive life may be very common in the universe, at least on planets with liquid water. There are also moons in the outer solar system with liquid water under their icy surfaces, including Jupiter's moon Europa and Saturn's moon Enceladus. And there are these geysers on the surface of Enceladus near its south pole. And the Cassini spacecraft actually went through the geysers and collected some of this water, but they never imagined that there would be some chance to see evidence of life, so they didn't have the capability to analyze it for complex organic molecules. On Earth, it took another 2 billion years after the formation of this early primitive kind of life for complex eukaryotic cells to develop with internal structure, nuclei and mitochondria and so forth. And complex multicellular creatures evolved only about 500 million years ago, the so-called Cambrian explosion. So intelligent life and science only arose once on Earth. It may be very rare. New space observatories may make it possible for us to detect the effects of life on distant planets, for example, through atmospheric composition. And we'll also keep searching for messages, and the huge square-kilometer array of radio telescopes being built in Australia and South Africa will help. So let me conclude. Without dark matter, we wouldn't exist. With only the ordinary matter, the universe would be a low-density, featureless soup. Dark matter started to form structures very early. Galaxies formed within bound halos of dark matter, stars formed within galaxies, and stars made elements beyond hydrogen and helium, the stuff that we're made of. Rocky planets formed from these heavier elements. Life began and evolved on one such planet. So dark matter is our ancestor and our friend. But science is much stranger than fiction. Before the discovery that most of the density of the universe is invisible, no one imagined this. What else remains to be discovered? Thank you.
Thank you very, very much, Professor Primack. It's absolutely brilliant presentation. I think everybody was so quiet and questions didn't turn in until very late. I think everybody was mesmerized by your talk. So thanks very much. There are quite a number of questions, and if I may read them some to you. You might like to sip some water before answering some of the questions. Here are questions that is related to shapes of galaxies. So I'll just combine a number of questions that are relevant to that. There's one from Ankita from India, and also similar question from Hermawan from Indonesia. Why galaxies come in different shapes and why they have a bulge at the center? So would you like to reply to those questions first before
Sure.
Okay.
Well, galaxies evolve, and besides the phenomena that I described, forming along filaments, you also saw in the visualization of that forming prolate galaxy that there are a number of mergers. The average galaxy since redshift 2 has suffered at least one major merger, in other words, a merger with a comparable mass object. And at earlier redshift, probably several such mergers. And those mergers can considerably perturb the shape of the galaxy. One of the ways that the bulges form is that gas is driven into the center during these mergers, and then the centers of the merging galaxies also merge quickly because of a process called dynamical friction. Mm-hmm. And the result is that a lot of mass is formed at the center. So the way a lot of this mass forms is gas flows into the center because it loses angular momentum. And that can happen for several reasons. Sometimes the gas is coming in simultaneously in two different directions and it collides. Often it's because gas is brought in by a merger. It can be a minor merger or several minor mergers. So galaxies have a rocky existence, especially in the early universe, where galaxies were much closer together. As the universe evolves, as I showed right at the beginning, the galaxies tend to fly apart. The material that would have hit the galaxy often is now driven away by the dark energy. And so the galaxy shapes don't change that much. Also, the universe is running out of gas. The afternoon stage of the universe, where there's much less star formation, is a period when the smaller galaxies continue to evolve fairly rapidly and form stars, but the larger galaxies have largely finished much of their star formation, although it will continue at a slow rate for many billions of years. Next question.
Okay, thank you. Well, there's still a question regarding galaxy evolution with merging. This is from Bajai from India. Galaxy evolution is more or less attributed to galaxy mergers, as shown in the simulation. Doesn't this make the evolution more probabilistic, considering our current understanding of the merger rate?
In fact, the rate at which galaxies merge is something that we can calculate theoretically from these kinds of simulations. And we can also measure it. But it turned out that a real difficulty in converting the observations to the merger rate is that you have to take into account very carefully the period during a merger when the merger can be detected. For example, you can detect a merger by seeing two galaxies close together, or by seeing a galaxy perturbed in certain ways, tidal tails, for example. But you have to calibrate carefully over what timescale you can see these things. And it turns out that in the early universe, the timescales are much shorter. So you have to take that into account, together with the data, for example, on how often we see galaxies close together. When you do that, there's actually good agreement between the observations and the predictions. Now, we also used to think, I used to think until about 15 years ago, that much of the star formation in galaxies, especially in the early universe, is driven by mergers. That turns out not to be the case. The reason is that in the early universe, galaxies are converting gas into stars about as efficiently as they can. And there isn't a lot of gas left over, so that when galaxies merge, that gas quickly gets converted into stars. The star formation rate can be elevated a little bit. But remember this main sequence idea, that most of the stars, most of the galaxies of a given stellar mass are forming stars at about the same rate. There aren't really large excursions. Occasionally we see particularly bright examples, but they're quite rare. So it turns out that much of the evolution of galaxies is not governed by mergers, although the shape evolution has more to do with mergers. But the rate at which stars form is not so much governed by mergers.
Thank you. It's sort of settling to live in a world not entirely probabilistic. And there's one more question that has to do with the presence of dark matter, but this is the counter example. Do the simulations predict existence of galaxies that are completely dark matter dominated, having no stars at all?
Oh, sure. The vast majority of dark matter halos will be low mass dark matter halos, which should have almost no stars. The reason is that if these halos form after reionization, at redshifts of 6 to 7 or so, even a little bit earlier, the gas is being heated up to a high enough temperature that the gas could not be retained in these small dark matter halos. The escape velocity from the dark matter halos is less than the thermal velocity of the gas. So only if the galaxies formed very early would, before reionization, would you expect to have any. And even then, there's a minimum mass of dark matter halos that could host a galaxy, somewhere around 10 to the 5.5 or something like that, solar masses. So the vast majority of dark matter halos should in fact have no stars at all. And at the low end, the whole process is probably very stochastic. Early stars drive gas out, and then depending also if you're near a big galaxy, that galaxy will be surrounded with a lot of gas, and if the gas has been driven out, it will be stripped away. So all of this is taken into account in high resolution simulations. The FIRE group in particular, feedback in realistic environments, has shown that they can rather nicely reproduce the evidence on very small galaxies around large galaxies. So I don't think that that's a particular problem. There were a number of things that a number of questions that people raised, like the too big to fail question that my former student James Bullock and his friends raised, and the core cusp issue and so forth. But I think most people agree now that these are probably largely resolved when you take the effects of star formation and gas physics and so forth into account.
Thank you. There's there are questions regarding dark energy. And so what actually is the role of dark energy? And there's also, what is that little bump at the transition period, which is very brief, but it seems to be very effective in perhaps resolving the Hubble tension?
Yes, so in the standard simulations that I've run, I simply assume that the dark energy is a cosmological constant, this idea that was introduced by Einstein just after he invented general relativity in 1915. He applied it to the universe and discovered that the universe could not be stable. It has to be expanding or contracting. And he didn't like that, although of course there was no evidence at the time. We didn't even know that there were distant galaxies. That was a discovery by Hubble a decade later. But Einstein thought, well, maybe if you put in a cosmic repulsion that would be consistent with all the data that they had, it could counteract the effect of gravity and produce a stable universe. That turns out not to be true, because if there's any inhomogeneity in the distribution of mass, it won't be stable. But in any case, he did introduce this idea, which fits nicely into general relativity, by simply abandoning one of the 5 postulates he made in his 1915 paper, namely that it had to agree exactly with Newtonian physics in the low velocity limit. And that allowed him to introduce this cosmological constant idea. And that turns out to very nicely fit the observational evidence of the expansion history of the universe, the distance versus redshift relation. It's possible that the dark energy is something more complicated, not just a cosmological constant. It may vary in time and even in space. And there are very big programs now. The Dark Energy Search, the Dark Energy Spectroscopic Instrument, the Euclid satellite that the European Space Agency is going to put up in a couple of years, and many other programs of this sort, to try to discover the nature of the dark energy. Has it changed at all? In which case it's not a constant. Or is it just a cosmological constant? So the fact is, we don't know what the dark matter is. We don't know what the dark energy is. And there are many very fundamental questions left to be resolved. As to that little bump at about redshift of 4,000, that, if there was one episode early in the universe at the Big Bang where dark energy played a huge role and caused inflation, and there's now a period when dark energy is playing a huge role on very large scales, maybe there was an intermediate period when there was a brief episode of dark energy that naturally goes away, just the way inflation did. That's an idea that was put forward in 2002 by one of my former students, Kim Greist, that there might have been multiple episodes. And why not? And I think it was Mark Kamienowski who appreciated that that could be a way to resolve the Hubble tension. And so I started collaborating with my old friend, Mark Kamienowski, and his group. And what we realized was that nobody had done the n-body simulations to see what the implications of this early dark energy picture would be. And we discovered, as I said, that it has major implications for earlier structure formation.
Yep.
So it makes lots of predictions that are directly testable. Let's see if any of that's right. So one thing that the students at the school should appreciate is nothing in cosmology is definitively discovered yet. The whole thing is a bunch of open questions, and there's many opportunities to contribute.
So infinite questions for them to work out, right?
Yes. I'm not sure if it's infinite, but it's enough to keep us thinking for a long time.
For a long time. There's one question that has to do with instruments, especially that we don't know how far its look-back time is when dark energy plays its role now and again. But how do you know that the images that one gets from the telescope is the real one, because of the many uncertainties that comes in? And then you probably put that into your simulation as an input. Would you care to comment?
Actually, it's more the other way around. The simulations predict much more information than we can ever get from the observations. Mm-hmm. So the usual tendency has been, in fact, to try to convert observations into theory space, work out things that are easy to predict from simulations, like the stellar mass of galaxies. The problem is that it is somewhat, I don't think there's any question that the images are what they are. Different telescopes looking at the same wavelengths will see the same images. The question is to interpret those images and convert them into things like stellar masses and star formation rates and so forth. And the reason that's complicated is that the light that we're using has gone through dusty media, and dust scatters light and it can absorb light and then re-radiate the energy at longer wavelengths. And often we can't detect those longer wavelengths. So we have to correct for all of these things. And there are many different approaches. Fortunately, in many areas, we have several different ways to determine what's actually happening. But the approach that I'm favoring, and I'm trying to use more and more, is to use the simulations, especially high resolution simulations, to make very detailed predictions of what the galaxies should look like, and then compare those systematically to all the images we get of those distant galaxies. And as I said, with better telescopes, James Webb is a much better telescope than Hubble, much bigger collecting area, much better cameras, able to see much further into the infrared, also with a much better spectrograph than we've ever had in space, the near spectrograph. So it's going to be an absolute gold mine of new data. And we hope it will actually go up and start producing data next year. It keeps being postponed, and the latest postponement is because of the COVID crisis.
Yeah, but that probably gives you more time to do simulations that to direct observations.
Simulations. I want to see the data. The trouble is that, of course, you can simulate all you like, but simulations are only predictions about what might be true. It's the observations that are the truth. Right. So the most effective way that science progresses is a dialogue between theory and data. And we always need more data. We never have enough.
Agree. Well, there are more questions, but we haven't got time to do everything. We'll collect everything and then put them into our questions library, and then perhaps we respond to them offline. And okay. And some of them would be actually answered in the following lectures.
I assume so. There are a number of lecturers that whose work I admire, and some of them are old friends, like Taran Sardeep. So hello to my old friends.
Will do. Thank you. Well, thank you very, very much, Professor Joel Primack. I think we arrive at the end of our lecture. But before the very, very end, we like to invite everybody to turn on their video so we can have group pictures for all of us. So there are 120 altogether. So there's going to be layers upon layers of pictures. So everybody's, please turn your video on. So we'll take pictures. And you can wave to each other now. Okay, I think, Anton, you ready to take pictures?
Yes. Okay, I will start to take a picture.
Excellent.
There is 3 slides, so maybe, yeah, I will take 3 of them. Okay, okay, please wait. Okay, 1. Okay, for slide 2, let's wait. Okay, be ready for slide 2. Okay. Okay, now slide 3.
So happy to see all of you.
Yes, thanks for joining us here, everyone. Okay, done.
Thank you.
Thank you.
Excellent. So we are ready to see the 13.7 billion years of universe history in the next 2 weeks.
Thank you very much.
Thank you. See you very soon. Bye.
Thank you very much.
Thank you very much. Bye.
Thank you very much.
Thank you.